viewers to another episode on ASU G12 exams. So in this episode we are looking at section B of the 2021 GCE Science Paper 1. So let us start with question B1. Laboratory safety rules and the regulations are important to keep laboratory safe. Question A. State the immediate action that a learner should take if the following happened while carrying out an experiment. Roman numeral 1. Chemicals got into contact with his or her clothes or skin or mouth. So basically what you are required to state is, in this case, the immediate action. So what should be done there and then. So for Roman numeral 1, basically when chemicals get into contact with basically clothes, skin or mouth, the immediate action should be taken is basically to wash off immediately with distilled water. So basically wash off the affected part immediately with water. Now this water should be distilled water or pure water, and report the accident to the teacher. That's basically what should be done. So immediately you need to wash off the affected part with water and report the accident to the teacher or a lab attendant. Number 2, she or he bent or cut herself or himself. So basically what is happening in this case, there is an indication of the opening of either the wound or the blood is flowing. So basically what happens in this case, immediately wash the wound with warm water and soap. So this one helps to remove potential bacteria or germs, and report the accident to the teacher or laboratory attendant. No matter how minor it may seem to appear, you need to report it to basically the one in charge. It could be the laboratory attendant or the teacher. So basically these are the immediate actions. Question B. The following diagram shows a Bunsen burner, the most commonly used heating apparatus in the chemistry laboratory. Give one reason why the air or should be fully open when the Bunsen burner is in use. So basically this is the all we are talking about. So why should it be opened in full? So basically when it is opened in full, basically it allows more inflow of air. So allows more inflow of air, resulting in more oxygen, which is required for a complete combustion. So once we have more air inflows, we're going to have more oxygen, which is basically will enter the Bunsen burner and hence support complete combustion. So basically that's the purpose. Let us look at question C. One of the gases used in a Bunsen burner is methane. Roman numeral 1. State all products of combustion of this gas in the Bunsen burner when the air ore is fully open. So basically if you see, methane is given by CH4, which is an hydrocarbon, and this is basically a gas. Then this, when burnt in air, it reacts with oxygen, which is a gas, to give us basically carbon dioxide. Because it's fully open, then there is complete combustion. So it's going to give us basically carbon dioxide, which is gas, plus water. which is basically a liquid. So when there is incomplete combustion, which is in the presence of a limited oxygen, we're going to have a carbon monoxide plus water. So this one becomes a monoxide because our oxygen is limited. Then we are required to state all the products from this combustion. So we know the products are two. So basically we have water and carbon dioxide. These are the products. So we have water and carbon dioxide. Let's look at Roman number 2. One of the products of complete combustion of methane is a pollutant. Name the product and state its effect on the environment. So one of the products which is basically pollutant in this case is carbon dioxide. This is water, which is not a pollutant. So here the name is basically carbon dioxide. Then what is its effect on the environment? So basically excessive carbon dioxide in atmosphere lead to global warming. That's why you hear they've been talking about limiting on combustion of these petroleum by promoting clean energy to reduce on global warming. So basically this is how you answer this question to get the 6 marks. Question B2. Figure B2.1 shows a separation technique used to separate miscible liquids. So if you look at the diagram, basically we have the thermometer, fractionating column, glass beads, anti-bumping granules, then we have the mixture of miscible liquids, then we have water in, a distillate, rear bank, condenser, then water out, then stand. Question A. What is the name of the separation technique? So if you look carefully at this one, you notice that basically this is a fractional distillation. So fractional distillation is basically the method used to separate a mixture of miscible liquids. So basically these miscible liquids, they have different boiling points. So it's these different boiling points which are key to separating these liquids. So in most cases we discover that these liquids that are being separated should have at least basically the interval of around 20 degrees Celsius apart in terms of boiling points. Let us move to question B. What is the purpose of the glass beads in the fractionating column? So the glass beads are here. So what is basically its purpose? So the purpose of these glass beads is basically to provide a large surface area for hot vapors to cool and condense repeatedly. So that's the purpose. So basically what you notice here is this is key because glasses are chemically very stable. So when you put these glass beads, they will not react with most of the substance. So because of this, I will discover that the collected liquids will remain intact in its pure form. Glasses are rarely reactive. We move to question C. Why is the rear big condenser kept in the slanting position as shown in figure B2.1? So why is this kept in this slanting position? That's what we are required to explain. So what you notice here in this case, if you go to C, these are basically allow gravity. So it's to allow gravity to move the liquid distillate to a separate flask or basically a beaker. So what will happen is because of this slant positioning, this vapor, once it condenses, it will move easily down to here. If it was upward, the liquid will come down inside. If it is just straight, there will be no pressure to go this direction. It's most likely to start going backwards. So this slanting position allows it to move down here easily. That's basically the purpose. Let us look at question D. Apart from the mixture of miscible liquids, name 2 other mixtures which can be separated using this separation technique. So basically the first one would be basically crude oil. So crude oil is basically separated using fractional distillation. So you separate basically kerosene, petrol, diesel, and basically you also get a bitumen from crude oil. Number 2, also you can separate liquid air using a fractional distillation depending on their boiling points. So different liquid air, they have got different boiling points. So this method can be used. Number 3, also you can separate ethanol and water using this method. So this method is very important in chemistry because it is used in the separation of a number of products that are manufactured in industry, basically using chemistry. So basically this is how you answer this question to get the optimal marks. Let us look at question B3. 2.0 grams of pure magnesium ribbon reacted with exactly 100 centimeter cubic of 2.0 molarity of hydrochloric acid. Construct a balanced chemical equation for the reaction including state symbols. That's question A. So what we have is basically magnesium and 2.0 moles per decimeter cubic, which is molarity of hydrochloric acid. So basically we know that magnesium ribbon is basically solid. So this solid it reacts with basically hydrochloric acid, which is basically an aqueous solution. So hydrochloric acid is like this, and this is aqueous solution. Then what are we going to get? So because magnesium is more reactive than hydrogen in hydrochloric acid, then it's going to replace it and it's going to form magnesium chloride, and this will be aqueous solution. Then plus the replaced hydrogen will be a gas. So basically this is what we are going to have. But remember, the question is asking us to do a balanced chemical equation. So now we need to ensure that this is balanced. That's the next step. So we start with basically hydrogen. This side we have 2 hydrogen. Here we have 1. So how can we balance? We introduce a 2 here, so that we have 2 hydrogens to the left hand side and 2 hydrogen to the right hand side. Then the hydrogen as balanced. We look at chlorine. We have 2 chlorine on the left hand side, and we also have 2 chlorine on the right hand side. So that one as balanced. In terms of magnesium, we have 1 on the left hand side and 1 on the right hand side. Then just by using one number, the entire equation as balanced. So basically you have a balanced equation. So on this one, it means you are done. You get the 3 marks. We move to question B. Determine the limiting reagent for the reaction. So we are looking for the limiting reagent between magnesium and the hydrochloric acid. One would be finish faster than the other one. So the one that finishes faster than the other one is a limiting reagent. Then the one which remains at the end of the reaction is excess reagent. So for us to answer this question, the first thing that we need to see is basically know the ratio in which these moles are used. So the moles are used in basically this is 1. There is 1 mole of magnesium here. So this is a mole. Then here there are 2. So for every 1 mole of magnesium, based on the balance equation, we need 2 moles of hydrochloric acid. That's what we need to know. Then this will give us 1 mole of magnesium salt, then 1 mole of hydrogen. So to find this, determine the limiting reagent, we just look at the left hand side, the ratio in which magnesium, ribbon, and the hydrochloric acid are used. So the next step, what you do is basically you see what we've been given. So we've been given the mass of magnesium, ribbon, and the molarity of hydrochloric acid and the volume. So what we need to see is compare the moles that we've been given. Compare this to this ratio, whether it's the same. So the first thing that we do is let us find the moles in magnesium that we've been given. How many moles are these? So to find moles we'll use a small m. It's basically a given mass divided by relative molecular of this element, which is magnesium. So we can easily find the relative molecular mass of magnesium on the periodic table. So what we do is 2 grams. Then we go to the periodic table. Once we go to the periodic table, we find magnesium is here, which is the mass number is 24. So the relative molecular mass of magnesium is 24. So when you divide that, we end up with basically 0.08332 4 decimal places. These are moles. Then similarly, we find the number of moles in hydrochloric acid from the information that we've been given. So to find the number of moles, we use the fact that basically we know that molarity M, capital M, is given by a number of moles divided by volume. So to find the number of moles, we just multiply moles is equal to basically molarity, then multiplied by the volume in basically decimeter cubic. So this is molarity, which is the number of moles per given volume, which is in the decimeter. So molarity is basically 2 from here, which is moles per decimeter cubic, then multiplied by what is the volume of this under this centimeter cubic in decimeter or liters. So we divide by 1000 because there are 1000 centimeter cubic in 1 liter. Then you end up with basically 0.2. Just to make sure that you multiply by 0.1, then you end up with 0.2 moles. So these are the moles that we have. But we know now that if we have 1 mole of magnesium, we need 2 moles of hydrochloric acid. Then if now we have this 0.2 moles of hydrochloric acid, how many moles of magnesium do we need? So here what we do is I'll just write on top here, if you have 0.2 here, which is just multiplying this by 0.1, this one, then here we also need 0.1, so that this ratio 1 to 2, it remains 1 to 2. But what you notice here in this case, we only have 0.083, which is less than the 0.1 we want. So because of that, you know that this is lower than what is required if we have this amount. So in this case, you notice that the limiting reagent in this case is basically magnesium. So magnesium is the limiting reagent, because if we have 0.2 moles of hydrochloric acid, we need 0.1 moles of magnesium to react with this amount, but we only have this one, which is less than 0.1. So basically, this is how you answer this question. Let us look at question C. The volume of the gas that was evolved. So the question is asking now to calculate the volume of the gas that was evolved. So what is that gas? So we know that from the output we only have one gas, which is basically hydrogen. So now to calculate the volume that was evolved or the product, what you need to use is you use the limiting reagent, which is less in supply, because remember hydrochloric acid is reagent in excess. Then it's this one which will determine magnesium, which will determine the output. So if in this case 1 would give us 1 mole of hydrogen, so if you have 0.0833 moles of magnesium, this will also give us 0.0833 moles, because this is 1 to 1. So now it's these moles of hydrogen that we need to convert to volume. So when you go to the periodic table, we discover that for every 1 mole of a gas at room temperature and pressure occupies 24 decimeter cubic. So now what we are saying is we don't have 1 mole, but we have 0.0833 moles. So now what we do is convert these to the moles. So 1 mole occupies 24 decimeter cubic. Then what is the volume would be occupied by 0.0833 moles. So what we do is cross multiply. So we have x times 1 mole is equal to basically x. Then we multiply by 0.0833 mole multiplied by 24 decimeter cubic. Then this mole and this mole cancels, so we remain with basically x is equal to, we multiply that. Once we multiply, we are going to end up with about 2.0 decimeter cubic to basically nearest whole number. So basically this is the volume that will be occupied by the gas produced, which is basically hydrogen gas. So basically this is how you answer this question to get the 7 marks. Let us look at question B4. Question A. Table B4 contains atomic mass units and percentage abundance for element Q. Determine the relative atomic mass of element Q. So and this basically carries 2 marks. So basically what we need to do for last to determine the relative atomic mass, we need to multiply the atomic mass unit, which is this one, by the percentage abundance. So what you notice, if you add these two, this will give us 100%. So ideally, when you're asked to find or determine the relative atomic mass of any given element, you are asked to find the weighted atomic mass unit. So basically the first thing that you do is basically multiply atomic mass unit by the percentage abundance. Then you need to add these corresponding. So what this happens is we have basically this one, which is 107 multiplied by this converted to percentage, which will be basically 52 over 100, then plus this one, which is 109 multiplied by the 48 divided by 100, because we want to convert it to 100 so that it's in decimal places. So what we end up with is basically 107 multiplied by 0.52, which is the same as 52%, plus 109 multiplied by 0.48, which is the same as 48%. Once we add this, we are going to end up with 107.96. This will be basically the relative atomic mass of element Q. This is how you get the 2 marks. We go to question B. Describe a radioisotope. And this is 1 mark. So basically, a radioisotope is also known as unstable nucleus. So it's that nucleus which is unstable. You know that a nucleus is stable when basically you have protons and electrons are equal, and also you have basically neutral charged neutrons. So when you talk about a radioisotope, you are saying basically this is an unstable atom that break down. So it does break down, giving out radiation. So if you have basically an atom that is unstable, that is able to emit radiation, that is known as a radioisotope. So in other words, it's basically an unstable nucleus. That's what it means. Let us look at question C. State one use of carbon-14 isotope. So carbon-14 isotope is basically used in carbon dating. So this is basically determining the age of fossils. So in determining the age of fossils, you use a carbon-14 isotope. So what happened basically is you look at the amount of carbon-14 isotope present in a given fossil, then you observe at the rate of decay, then you're able to backdate and determine the age of a given fossil. Number 2, Roman numeral 2 of C. What's the use of iodine-131 isotope? So this is basically the same state. So basically this is used in medical science for basically diagnosis and treatment of cancer and tumors. That's the use of iodine-134 isotope. So basically this is how you answer this question to get the full 5 marks. Let us look at question B5. Fluorine gas is bubbled through a solution of potassium bromide as shown in the diagram below. Describe what would be observed in the test tube. So basically what you notice here in this case, we have a solution potassium bromide, then we have a fluorine gas which is bubbled through that. So what are we going to observe? So what we are going to observe is white powder or crystals will be formed. So we are going to see that a white powder or crystals will be formed in this test tube. So basically this will be a confirmation that a single displacement reaction has occurred. So basically what is a single displacement reaction? So this is basically referred to a chemical reaction in which a more reactive halogen displaces a less reactive halogen in a given compound. So when you go to the periodic table, what you observe is basically fluorine, which is upper, is more reactive than a bromine gas, because the activity of halogen increases as you go up the group. So this is what is going to basically happen. Let us look at question Roman numeral 2. Write a balanced chemical equation for the reaction that occurs in the test tube. So what we have is basically fluorine, which is a gas. Then this react with potassium bromine, which is in solution aqueous. This will basically give us potassium fluoride, which is a crystal, so there will be solid, then plus basically bromine gas. This will be basically the equation, but we need to balance it. So what you notice on the right hand side, we have 2 bromine. Then on the left hand side, we only have 1. So we need to balance. So what you can do is we can introduce a 2 here, so that we have 2 bromine on the other side. Then what you notice here in this case, of course, we have 2 bromine balanced, but we have 2 potassium on the left hand side and only 1 on the right hand side. So what we do is we introduce a 2 here so that they balance. So what you notice here in this case, we have 2 potassium balanced. Then we also have 2 fluorine on the right hand side and also 2 fluorine on the left hand side. So here what you notice in this case, the equation is balanced. So this is how you get the 2 marks. Let us move to the next question. Question B. What would be observed in the test tube if iodine gas was bubbled through the potassium bromide solution? give a reason for your answer. So before we answer, let us go to the periodic table so that we see as we give the reasons. So in this case, we are bubbling now iodine in the bromine solution. So we discover that iodine is less reactive compared to bromine gas. So in this case, iodine cannot displace a bromine. So what you notice is there will be no reaction at all. So you're not going to observe anything happening in the test tube. So basically no reaction would be observed. Reason this is because iodine gas is less reactive than a bromine gas in the reactivity series of halogens. So single displacement won't occur if we introduce a more reactive halogen than the one that we have in the solution or a compound. Otherwise, nothing will be observed. So basically, this is how you answer this question to get the optimal 7 marks. Let us look at question B6. Question A, describe the rate of a chemical reaction. And this is basically 1 mark. So what you notice in this case, the question is asking us to describe. So basically just telling us to say what it is. Define what it is. What does it mean when you're talking about a chemical reaction? That is the key there. So basically when we're talking about a chemical reaction, we're talking about basically the measure. So it is a measure of how fast reactants are consumed and products are formed. So basically, in other words, what you are saying is basically it is the speed at which the chemical reaction proceeds to produce the products. That is what the rate of a chemical reaction implies. We look at question B. State a reason for each observation below. Roman numeral 1. Hydrogen peroxide decomposes much faster in the presence of enzyme catalase. So we need to state a reason. That's what the question is giving us. So the reason is basically why is it that hydrogen peroxide decomposes much faster in the presence of the enzyme catalase? That's what you need to explain. So basically what we notice here is these are catalase acts as a catalyst. That's what it acts. So basically a catalyst is basically a substance which increases the speed of reaction without being changed or used up in the reaction. That's what basically it is doing. So if we now to define what a catalyst is, we are saying is a substance which increases the rate or speed of reaction without being changed or used up in the reaction. That's what you are calling a catalyst. So what you notice in this case basically this catalase is acting as a catalyst. That's why basically the decomposition is much more faster. We move to Roman numeral 2. The reaction between manganese carbonate and dilute hydrochloric acid speeds up when some concentrated hydrochloric acid is added. So why is it that the reaction between manganese carbonate and dilute hydrochloric acid speeds up when some concentrated hydrochloric acid is added? So basically the answer is the concentration of acid is increased, so the reaction rate increases too, because of the fact that we have this. Okay, because of once we increase the concentration, basically what is going to happen is the overall concentration of basically the acid increases, which in turn increases the rate of reaction. So the higher the concentration, the more the number of moles per liter. So if you have more number of moles per liter, then that would mean manganese carbonate will have more moles to react with, hence the rate of reaction increases. That is basically what is happening. We look at Roman numeral 3. Powdered magnesium is used in fireworks than the magnesium ribbon, because remember the question is for us to state the reason. So in other words, the question is, why is it that powdered magnesium is used in fireworks rather than magnesium ribbon? So basically the answer is the powder has much large total surface area than the ribbon. This ribbon magnesium, hence it burns much faster. So basically this is how you answer these questions to get the total 7 marks. Let us look at question B7. During the extraction of zinc, the ore is first roasted in air as illustrated by the equation below. Question A. Give the common name of the ore in the equation above. So basically we are looking for the common name. So this common ore is basically known as the zinc blende with E. So this one basically contains zinc sulfide, this ore. So this is the part you are seeing here. That's the zinc blend we are talking about. This is basically N. Let us look at question B. Name the substance which can be used to reduce zinc oxide. So we want to reduce zinc oxide, which is obtained as one of the product. So basically what can we use? So basically zinc oxide is reduced by basically carbon monoxide. So carbon monoxide is basically used to reduce zinc. So once you reduce this one, basically it will give you two products. Okay, so at the end of the day, you're also going to get carbon dioxide. So what happens is basically you react zinc oxide, which is solid, with basically carbon monoxide, which is gas. Then what you end up with basically is zinc, which is solid, then plus carbon dioxide, which is gas. So what you notice on the reactivity series, zinc is less reactive than carbon. So carbon is able to displace zinc from here, so that zinc remains to be a pure product. So basically this is what happens. We move to question C. Suggest a reason why sulfur dioxide should not be allowed to escape into the atmosphere. So basically what you notice here in this case is we are just giving a reason. That's what the question is asking us to do. So basically what you notice here is sulfur dioxide is a common air pollutant. That's why it is a common air pollutant. So that's why we should not allow it to escape into the atmosphere freely. So basically what it does is when it reacts with rains, it produces basically rain acids, because it's readily able to react with water to create sulfuric acid, which basically is the rain acid. It also irritates the eyes and hence causing also breathing difficulties. When you breathe it, breathing difficulties. So that's why we are supposed to control or minimize its basically accumulation in the air. So one way to minimize or control its escape into the atmosphere, what you do is basically you are going to treat basically this gas with wet calcium hydroxide, which basically will be able to remove our sulfur dioxide. So basically that's one measure that you are going to use to minimize its escape into the atmosphere, in case you came across such kind of a question. Question D. State one use of zinc. So zinc has got a number of uses. One of them is basically used in galvanizing. So galvanizing of basically steel and iron. So this is basically which is a way of creating a protective coat to prevent rust. Then in case the question said more than one, it is also used in making of brass and bronze alloys. Then number 3, just to add more, it is also used in basically extraction. So it helps in extraction of gold and silver. So it's used in the extraction of gold and silver, as zinc is more reactive than these elements. The fourth one, bonus one, it is also used as electrodes in amalgamated form. So these are some of the key uses of basically zinc. Then the bonus one, it is also can be used for the reduction of phenol to benzene, as it act as a reducing agent in the form of zinc dust. When it is zinc dust, you can use it to reduce phenol to benzene. So basically these are the key uses that you need to know of zinc. Let us look at question B8. The structure displayed below is a polymer that was formed from monomer Y. Name the polymer. So the question is asking us to name the polymer, which is this one, formed from monomer Y. So to name the polymer, the first thing that we need to do is basically look at the polymer, then identify the repeating units. So once we identify the repeating units, it's much more easier for us to name this polymer. So we have this part, then we have this part. So what you notice, these parts are basically the same repeating. So this is basically, so we pick one a repeating unit called monomer, which is basically a small molecule, and count the number of C's. So we have 1, 2, 3, 4. So we have C4. Then basically there is no oxygen here, so these are hydrocarbons. So let us count the number of H. There are basically 8. So if there are 8, they conform to this formula, which is the alkenes. So this one tells us it's basically 4 carbons, so it's basically a butene because of alkenes. So now a polymer is made from the combination of small molecules called monomer. So it's this monomer that will give us the name, which is should be basically poly. Then we combine with this name, which becomes polybutene. So polybutene is basically the name of this polymer in a simple term. We move to question B, Roman numeral 1. Name the monomer Y. So the monomer Y, we have basically easily identified it from this formula, but this monomer can be written, can have different names. So in this case, at basic level, it will just be basically butene. Then if you want to basically move to a higher level, this, because of this, which is basically alkane minus 1. So once this one becomes CH minus 1H, CH, this becomes an alkane, which is methane. So because it's less, it will be known as to become this group. So this could also be done as a butene because of these repeating. Or alternatively, you can make it more specific because of this branch. So we have the longest straight bond, it will be 1, then 2, then 1 backward, then 2. So what you notice here, these are at the first. So because they are at the first C, you can write it basically as O2 butene. At basic level, this would be surface, but if you want to show more detail, you need to write this one or this one. You should be able to get the full marks. We move to question Roman 2b. Construct the displayed structure of monomer Y. So you just get this one the way it is. So as the repeating unit, so that's a repeating unit. So basically the repeating unit, what it has is basically it has CH3, then C, then CH, then this C, then this C, then C, this H, then this one, which is CH3. Now this one basically, to write it in these bonds, these two bonds, will give us a double bond for it to be basically stable or saturated to exist in this form. So these and these will form the double bond, which will be like this, then this. So this basically is the structure of the monomer Y. That's how you basically answer it. So you just get one branch of this, and because of this it forms double bonds. Double bonds closes this part. We move to question C. Monomer Y was reacted with steam under suitable conditions, and an organic compound Z was produced. To which homologous series does compound Z belong? So now we know that this monomer Y is basically an alkenes. So because it's an alkene, all alkenes are basically react with water or steam, which is this one, in the presence of a phosphoric acid as basically a catalyst at high temperature and pressure, and they give us alcohols. So when they react, they will give us alcohols. So basically these are the suitable conditions we are talking about. So the produced compound Z should be basically an alcohol. So these are alcohols. That's where they belong. Then C Roman numeral 2, write the general formula of homologous series stated in C1. So these are alcohols and they have this generic formula CnH2n plus 1. Then the hydroxyl. This hydroxyl is what forms the alcohol part. So basically this is the generic formula. So basically this is how you answer this question to get the 5 marks in full.